Hey, welcome back. On tonight's homework, we are doing some more mixed multiple choice questions that are going to be similarly worded to those that you'll find on the Calculus AP exam. The actual exam is going to have two multiple choice sections. Part A, which is going to be no calculator, has a total of 30 questions, and you get 60 minutes for those 30 questions. So you should be averaging about 2 minutes per question. And on the second part, which is no calculator, there are 15 questions, and you get 45 minutes to do those 15 questions. So you get to average about 3 minutes per question on that section. So as we go through these practice problems, I'm going to try to stick to those time limits. On this particular homework, there are only 11 no calculator questions. So if we're averaging 2 minutes per question, it should take us about 22 minutes to finish it. Hopefully I don't go over that, but as I'm explaining the problems, it's quite possible that I do go over. Also keep in mind that you don't have to stick to that 2-minute time limit per question, because some questions you're going to be able to solve faster than 2 minutes, and some will take a little bit more than 2 minutes. You just want to be averaging about 2 minutes per question. So let's get started with the no calculator questions. The first one is a limit question where we have the limit as x goes to infinity. And on these types of problems, you want to be thinking about the relative rates of growth of both the numerator and the denominator. In this case, we have a cubic function on the numerator and the denominator. So the rate at which this is growing is going to depend on the leading coefficients of both the numerator and the denominator. One thing we can do here is just kind of ignore all the terms that have a degree less than the largest degree of the polynomial. So we can say that this equals the same thing as the limit as x approaches infinity of just simply x cubed over 4x cubed. Now that's going to obviously simplify to be 1/4, and that's going to be the value of our limit. This limit as x goes to infinity is also equal to the horizontal asymptote of the function. So when we talk about horizontal asymptotes, and if we do ever, what we're really talking about are the limits as x goes to either positive or negative infinity. Number 2 says, at which of the 5 points on the graph are dy dx and d squared y over dx squared both negative? So the other notation that we can use for each of these are going to be f prime and f double prime. So they're just a different way of saying the same thing. Now, when we're talking about dy dx, or sometimes you talk about y prime or f prime, that's referring to the slope of the function. Okay, so we're going to be looking at whether or not the slope is positive or negative at each of these points. And when we start talking about the second derivative, whether we write it like this or like this, that's going to be referring to the concavity of the function. So let's just kind of go through each one of these points and see if we can't determine both the slope and the concavity. So let's first talk about the slope. The slope is going to be positive anytime you have an increasing part of the function. So for example, a here has got a positive slope. So does e. Those are both going to be positive slopes. So here y prime is positive, and y prime is also going to be positive at e. Now on point B and point C, we have negative slopes. So in these cases, y prime or dy dx would be negative. Now, it's not super obvious if D is for sure going to have a horizontal asymptote, but it sure does look like, or not an asymptote, but a tangent line. Sure does look like it though, so I'm going to just go ahead and say that y prime is 0 there. So as far as them both being negative, we've already ruled out half of the points here. We can see that it's either going to be B or C, because those are the only two places where the first derivative is negative, but we also need to consider whether the second derivative is negative. Now, the second derivative is talking about concavity. So when a function is concave down, like on the first half of this graph, you can see it's concave down from here to right about there. It's not super clear exactly where the concavity changes, where that point of inflection is, but that's a pretty reasonable estimate there. We can see both A and B have are on a portion of the graph that is concave down, and anytime the graph is concave down, we know that the second derivative is negative. The second half of this graph opens upward, and so we say that this portion right here is concave up, and any part of the graph where the graph is concave up, we can say that the second derivative there is going to be positive. So if we're looking for both the first derivative and the second derivative, maybe I should call these y instead of f so I can be consistent here. But anytime, the only point here that has a negative first derivative, meaning negative slope, and also a negative second derivative, meaning it's concave down, is going to be choice B. For number 3, it's the slope of the tangent to this curve, y cubed x plus y squared x squared equals 6 at 2, 1 is. Okay, so here this problem looks like it's not going to be too bad just at first glance, but you really do have to make sure that you are on top of your derivative rules here, particularly the product rule and the chain rule, because we are going to have to differentiate an implicitly defined equation here. And by implicitly defined equation, what I mean is it's not solved for y. So we are going to have to differentiate both the left-hand side and the right-hand side with respect to x. And that's how we're going to start this off. Now, when we do that, we see that the very first term, y cubed x, is a product. So we are going to have to use the product rule. And just a little reminder, the product rule is if your two functions are f and g, and we're trying to take the derivative of that, we need to differentiate the first function, multiply it by the second, and then add that to the product of the first function and the derivative of the second. So f prime g plus f g prime. So the derivative of the first here, y cubed, is going to be 3y squared. But since we're differentiating with respect to x, we do need to use the chain rule on y. So we need to multiply that by a y prime, or in other words, the dy dx. So you can write, maybe I'll write this in different color just to make it a little bit clearer that this is not y to the first power, but it's y prime. You could also write it as, like I said, dy dx. And so when we're talking slope, you could either write it as y prime or dy dx. Those are kind of interchangeable notations. But anyway, that's the derivative of that of y cubed. But using the product rule, we also need to multiply by that second function, which is just x. And then we have plus fg prime. So plus y cubed times the derivative of x with respect to x is just 1. So we just have y cubed times 1. So this expression right here is really just the derivative of this first product. Now for the second term, we have to use product rule again. So I'm going to say plus, and then product rule again, the derivative of y squared is going to be 2y times dy dx. Using that chain rule, we do have to multiply by the derivative of y times the second function here, x squared, and then plus the fg prime is going to be y squared times the derivative of x squared, which is 2x. So everything after this particular plus is going to come from the derivative of that second term. Now the derivative of 6 with respect to x, really with respect to anything, the derivative of any constant is just 0. So we're going to set this equal to 0. Now what we're trying to do is we're trying to solve for y prime here. So what we're going to do is take all the terms that have a y prime, which there are only 2 of them, this one and this one right here. I'm going to isolate those on the left-hand side of the equation and move all the other terms to the right-hand side. After that, we're going to factor out the y prime and then divide by whatever the other factor is. So let's take this step by step. First, we'll leave the 2 underlined terms on the left-hand side. And so I'm just going to write this as 3y. And actually, I'm going to move the y prime to the back end of the term, just to make it a little easier to read, plus 2yx squared times y prime. And then I'm going to move those other 2 terms to the right-hand side. So that'd be minus y cubed minus, and I'm going to bring the 2 out to the front just to, again, for aesthetic purposes, 2y squared x equal, I already moved it. So yeah, there you go. So now I want to factor out the y prime as a GCF, or a greatest common factor, y prime times 3y squared x plus 2yx squared equals negative y cubed minus 2y squared x. And so finally, to isolate the y prime, I need to divide both sides by that factor that it's being multiplied by. So y prime is going to equal negative y cubed minus 2y squared x, all divided by 3y squared x plus 2yx squared. So we've got our equation for dy dx, that's the slope of the line, and now we want to evaluate that at 2, 1. So we're going to plug in 2 for x, 1 for y, and just start evaluating here. So 1 cubed is just going to be 1, so we get negative 1. minus 2 times 1 squared. So 2 times 1 times 2 is going to be a minus 4. All over, let's see here, y squared is going to be 1. So 3 times 2 is going to be 6. Plus, let's see here, 2 times 1 is 2 times 4 is going to be 8. And so we get negative 5 over 14. And so our answer is C. And this is an example of one of those problems that is probably going to take you more than 2 minutes to solve, but there are going to be some that should take you less than 2 minutes. So when I say an average of 2 minutes on every problem, just know there are going to be a couple like this that are a little algebra intensive that will take you more than 2 minutes, and that's okay. You'll earn back that time on some of the easier ones. Like, for example, number 4 should take us much less than 2 minutes to figure out. It says, what is the average rate of change for this function? Now, this just comes down to knowing how to calculate the average rate of change. And so it's just a little formula here. It's basically just your slope formula. It's going to be f of 3 minus f of 0, 3 and 0 coming from the endpoints of the interval, over 3 minus 0. Now, you will have to evaluate both f of 3 and f of 0. That shouldn't be too bad. F of 3 is going to be 3 to the 4th power, which is 81. Minus 15 is 66. And if I plug in 0, I get 0. 3 minus 0 is 3. And so, yeah, 66 divided by 3 is 22. And see how that one took us much less than 2 minutes. So there are going to be some problems that take you more and some that take you less. Number 5 says, if f of x is sine squared of 3 minus x, then what's f prime of 0? So we do need to differentiate this, and this is going to require the use of the chain rule because we do have a composite function. And in fact, we do have 3 functions that are nested together here. I think on these sine squared, or anytime you've got like a trig function that's being squared or cubed or anything like that, where the notation has the exponent like right after the function, I would advise you to rewrite this and bring that to the outside. So in other words, rewrite this as sine of 3 minus x and then that whole thing squared. That's what it means anyway, but I think if you rewrite it like this, it'll be a lot more obvious what the order of the functions are. So the most outside function here we have is going to be quantity squared. And then we do have a middle function here, which is sine. And then our inside function is 3 minus x. So using the chain rule, we're going to take the derivative of the outside function and then leave the inside the same, and then do the same thing with the middle function, and then finally we'll take the derivative of the inside function. So f prime of x is going to be the derivative of something squared is 2 times that something. So this is going to be, and maybe I should color code this. We'll use green since that's how I highlighted that outside function. 2 times sine of 3 minus x. So that's the derivative of the very outside one, but times the inside, the derivative of the inside. So times, and I highlighted that in orange here. So the derivative of sine is cosine. So we have times cosine of 3 minus x. And then finally, we're going to multiply by the derivative of the inside. The derivative of 3 minus x is just negative 1. So here we have our function for f prime. The question's asking for f prime at 0. So we're just simply going to plug in 0 everywhere where we see x. So we have 2 times sine of 3 minus 0 is just 3. And then cosine of 3 minus 0, again, is just 3. Times negative 1. So I'm going to do that negative 1 times the 2 that's up to the front, changes that to a negative 2. And we have our answer. It is B. Number 6, we have a limit as x approaches pi. Okay, so for this one, you want to it's probably going to be L'Hopital's rule. If you get a limit problem that's not super obvious, it's probably going to be a L'Hopital's rule problem. But just to verify, and this is going to be how you have to show your work on the free response section. Anytime you want to use L'Hopital's rule, you have to prove that you actually can use L'Hopital's rule. Obviously, on a multiple choice section, that's not really necessary. But basically, what we want to do is find the limit as x approaches pi of the numerator and do the same thing with the denominator and show that both of those are 0. And if we can do that, then we can use L'Hopital's rule. You don't have to show this work on a multiple choice, but I want to just take a moment and show this work so you can see what is going to be required on the free response section. So if I plug in pi, cosine of pi is negative 1, sine of 2 pi is 0, And so we have -1 plus 0 plus 1 is 0. So yeah, sure enough, the limit of the numerator is 0. And if we plug in pi to the denominator using that direct substitution, we get pi squared minus pi squared, which is also 0. So since we have the limit of the numerator and the limit of the denominator both 0, we can use L'Hopital's rule. And L'Hopital's rule is a really convenient way of finding these limits. And basically the way it works is you find the derivative of the numerator, find the derivative of the denominator, and then try to use direct substitution. So this limit over here is going to equal the limit as x approaches pi of the derivative of the numerator. So let's go ahead and differentiate that numerator. The derivative of cosine is negative sine. The derivative of sine of 2x is going to be, well, using the chain rule, we're going to get plus 2 cosine x. And then the derivative of 1 is just 0, so that's it. The derivative of the denominator, derivative of x squared is going to be 2x, and pi squared is just a constant, so the derivative of that's just 0. You can see now that if I try to use direct substitution, I won't have any domain problem. I won't have any like divide by 0 problems here. So negative sine of pi plus 2 cosine of pi, running off the page here, that's okay. Divided by 2 pi, sine of pi is 0, so we have 0 plus 2 times cosine of pi is, what was cosine? That's -1. Times 2. So hold up here. Let's back that up a little bit. And, I see what I made a little error here. No big deal. But this should actually be 2 cosine of 2x. Yeah. Try to bypass a little u substitution here. Trying to do this quickly, and that's when mistakes happen. So we got a little, I can't even read that now. But that should be plus 2 times cosine of 2 pi, which would be 1. So we have 0 plus 2 over 2 pi, and the 2 divided by 2 is just 1. So that's going to give me 1 over pi, and so my answer is B. Number 7, once the limit as x approaches infinity of this rational function, or not really rational, but sort of a pseudo-rational function where you have a radical on top. And we're going to approach it kind of like we did number 1, where we're just really going to consider those biggest terms that are affecting the rate of growth the most. So we get the square root of 9x to the 4th over x squared. And when we take the square root of 9x to the 4th, we're actually going to get the absolute value of 3x squared over x squared. And so as x approaches infinity, this is just going to go to positive 3. Number 8 says the graph of the piecewise defined function f is shown at the figure below. The graph has a vertical tangent line at x equals -2, so we've got a little vertical tangent going here. A horizontal tangent line at -3 and -1, which means we have local extrema at these 2 points. What are all the values of x between -4 and 3 for which f is continuous but not differentiable? Okay, so it's not going to be differentiable anytime you've got a vertical tangent. Okay, it's not going to be differentiable anytime you have a discontinuity. Now in this problem, we want it to be continuous. So we don't even have to worry about that on this particular problem, but that would make it not differentiable as well. And then we also are going to be looking for sharp turns to, anytime you've got a sharp turn, the function is not going to be differentiable. So as far as it not being differentiable, it looks like there's 3 locations here where the function is not differentiable. It is not going to be differentiable at x equals -2. It's not going to be differentiable at x equals 0, and it's not going to be differentiable at x equals 1. Now, we don't want to report back 0 because we do have a discontinuity here. We've got a jump discontinuity, and so we don't need to report that one because we want it to be continuous but not differentiable. So the only 2 possible answers here are going to be -2 and 1. So our answer is C. Number 9 says an ice sculpture in the form of a sphere melts in a way that maintains its spherical shape. So this is going to be, I can already tell this is going to be a related rates problem. So I'm just going to make a little note that this is a related rates problem. Okay, we've got a sphere, which I'm not going to draw this super well. This is like pretty much how I draw spheres here. It's got a radius, we'll just call that r, and here's my drawing of a sphere. Looks a little messy, but it'll get the job done. It says the volume of the sphere is decreasing at a constant rate of 2 pi cubic meters per hour. So that little piece of information is telling us that dV dt, or the change in volume over time, is negative 2 pi. And the reason why it's negative is because it's decreasing. At what rate in square meters per hour is the surface area of the sphere decreasing? So it's asking for the surface area, the rate at which the surface area is decreasing. So what it's really asking is, what is, I'll call the surface area A, what's dA dt? So let's start with the volume formula here, which is given as 4/3 pi r cubed. And then when you differentiate that with respect to time, we get dV dt equals 4 pi r squared. 4 pi r squared dr dt. Now what this is going to allow us to do is it's going to allow us to find dr dt, which is what we're going to need to find the change in surface area. So dV dt, it gave us was negative 2 pi. So negative 2 pi equals 4 pi times the radius, which I guess I must have just read over that, but that's going to be 5. So 5 squared times dr dt. Let's see here. So 5 times 5 squared is 25. So that's going to be 100. 2 divided by 100, that's going to be negative 1/50th is dr dt. So we can use that in our area problem. So the surface area is 4 pi r squared, and that's given. So if we want the change in area over time, we need to differentiate both sides with respect to time, and we get 8 pi r dr dt. And now we have all the numbers that we need for this one. We've got the radius, which is 5, and we got the dr dt, which we just found was negative 1/50. Here, it'd be a little tricky. It's not as bad as it looks to do by hand. 8 times 5 is 40, so we get negative 40/50, negative 40 pi over 50, which reduces to negative 4 pi over 5. Now our answer is A, although you might be wondering why it's positive 4 pi over 5 instead of negative, and it's because the way the question's worded is saying, what is the rate at which the surface area is decreasing? So there's an implied, it's implied that it is decreasing, so that negative is implied within the problem. So it's decreasing at a rate of 4 pi over 5. What would those units be? I guess that'd be meters squared per hour. It's decreasing at that rate, and so it should make sense that the actual numerical value there is negative 4 pi over 5. Okay, number 10 says the functions f and g are differentiable, and g is the inverse of f. So if g is the inverse of f, then we want to know the derivative of g. G prime is going to be 1 divided by f prime of g. Now, that's just your inverse derivative, the derivative of an inverse rule. That is something you're going to need to know to get this question right. So if we want g prime of negative 3, that's going to be 1 over f prime of g of negative 3. And this value is going to be given, this g of negative 3 is given in the problem. It's 2. So we've got 1 over f prime of 2. And f prime of 2 is also given in the problem. F prime of 2 is negative 1/3. So this would be 1. There we go. 1 divided by negative 1/3, which is negative 3. So yeah, really just make sure, if you're not familiar with that derivative and inverse property, that you review that. This is the last multiple choice with no calculator problem that we have. It says if f of x is the integral from 1 to x cubed of 1 over 1 plus natural log of t dt for positive values of x greater than 1, or equal to 1, then what is f prime of 2? So we need to find the derivative of this, and that's what the fundamental theorem of calculus is for. So there's two parts of the fundamental theorem of calculus, one that we've used many times so far, which is when you find a definite integral from a to b, then you take the antiderivative of whatever you're integrating and then plug in the two limits of the integral. Here, this is the second part of the fundamental theorem of calculus, which is basically when you have a setup like this, you're going to plug in that upper limit into t. So what I'm going to say is that, how do I want to write this? F prime of x is going to be, let's clean that up a little bit. F prime of x is going to be 1, or the derivative of f is 1 over 1 plus the natural log of x cubed times the derivative of that upper bound, which is going to be 3x squared. So if I want to find f prime at 2, I'm just going to plug in 2 everywhere I see it. 2 cubed is 8. Then over here I have 3 times 4, which is 12. 2 squared is 4. So 3 times 4 is 12. And so I get 12 over 1 plus natural log of 8. Okay, so your answer is D, and that is it for these 11 questions. I think we're really cutting it close on time here. Again, we might be a little bit over here just because I'm trying to explain every problem as we go through them. So I'll have to double check the time because I know I'm really close there. So hopefully it works out okay. But yeah, that's it for the non-calculator problems for tonight. Let's go on and try some calculator problems. Number 12 says that the first derivative of the function f is defined by f prime equals sine of x cubed minus x for x values between 0 and 2. On what intervals is f increasing? Well, in order for f to be increasing, f prime needs to be positive. And so what we're going to do is we're going to graph f prime, which is this equation right here, and look to see where it's above the x-axis between 0 and 2. So in Desmos, unfortunately, you can't type in a function like this. Like it's gonna give you a little error message. You can't define f prime this way. So instead, what we're going to do is just type in sine of x cubed minus x. And we'll put on that little domain restriction so we can zero in on what we actually want to see, which are the x values between 0 and 2. And so we're going to see this little piece of the graph. And what we are interested in is this little piece right here, which is above the x-axis. And that's going to be in between 1 and about 1.691. And so our answer is B. Number 13 says, let f be the function with derivative given by f prime equals sine of x squared plus 1. How many relative extrema does f have on the interval? So relative extrema are going to be locations on the graph of f prime where f prime changes signs. In other words, f prime should be changing from either negative to positive, which indicates that you have a local minimum, or from positive to negative, which indicates you have a local maximum. So let's type in that equation, just like we did the previous one. We've got sine, and it's already kind of set up here. We're just going to change this to x squared plus 1. And on the interval, we're going to change that from 2 to 4. So we may need to zoom out a little bit. Just kind of scroll over here. And we can see that, we're going from, this is f prime, and f prime is negative changing to positive at this 2.29. It's not asking exactly for what that x value is. We're just counting up how many times this happens. But just to kind of point this out, since it is going from negative to positive, that means we have a local minimum on f here. We've got a local maximum here because it's going from positive to negative, another local minimum, and then a local maximum. So altogether, we've got 1, 2, 3, 4 relative extrema. So our answer is B. Number 14 says that the velocity in feet per second of a particle moving along the x-axis is given by the function v of t equals e to the power t, plus t times e to the t. What is the average velocity of the particle from time equals 0 to time equals 3? So the average value formula is going to be the integral from a to b of f of x dx over b minus a. And so what this gives you is the average value of a function between b and a. So if we want the average velocity between time equals 0 and time equals 3, we're just going to change this to be the integral from 0 to 3 of v of t dt over 3 minus 0. So we can just type this in. First, we'll type in v of t. So that way we can refer directly to it without having to type it within the average value formula. So v of t is e to the t plus t times e to the t. And so to calculate the average velocity, we're going to find the integral from 0 to 3 of vt dt. Notice that you can just type it like this, which is kind of nice, so you don't have to retype this whole expression, divided by 3 minus 0. I know that we all know that that's just going to be 3, but I like typing it in there like that just so that we've got it kind of set up the same way that we would set it up if it wasn't minus 0. So anyway, we get 20.086, and so our answer is C. Number 15 says, let f be the function defined by x plus the natural log of x. What is the value for c for which the instantaneous rate of change of f at x equals c is the same as the average rate of change of f over the interval from 4 to 1, or 1 to 4? So this is referring to something called the mean value theorem. Mean value theorem, which is going to guarantee that that point even exists in the first place. So first we're going to find the average rate of change, okay, because that's something we can calculate. The average rate of change is going to be calculated differently than the average value. The average rate of change is going to be f of b minus f of a over b minus a. It's just your classic slope formula. So in this case, it would be f of 4 minus f of 1 over 4 minus 1. And what we want is the x value, which is what we're calling c, where this number is equal to the instantaneous rate of change, which is f prime x. So we're going to just type this piece in to Desmos, and then we're also going to type in f prime after we type in what f of x is, and we're going to look for where these two things are equal. So first thing we need to type in is going to be the f of x. So f of x is x plus the natural log of x. We don't really need to see the graph of this particular function, but we will need to refer to it. So now we're going to calculate the average rate of change, which is f of 4 minus f of 1 divided by 4 minus 1. Okay, we don't even really need to make a note of this. We're just going to refer to this anyway. And so what we're going to do, this is a constant value, is we're going to create an equation, just y equals that. Okay, and notice it graphs this horizontal line. We don't need this graph anymore. And so what we're going to be looking for is where f prime intersects with that function. So if we have y equals f prime x, you see it's graphed here in red. There is a point of intersection right here at 2.164. So this is the place where the instantaneous rate of change, which is f prime, is equal to the average rate of change, which is this f4 minus f1 over 4 minus 1. So that's going to happen right here. It's 2.164, which is choice A. Number 16 says a radius, or the radius of a circle is increasing at a constant rate of 0.2 of a meter per second. What is the rate of increase in the area of the circle at the instance when the circumference of the circle is 20 pi meters? Okay, so this is a related rates problem. And so what we're going to have to do is write a couple formulas down and try to compute the rate that the area is changing. So what we really want to find, when it says what is the rate of increase in the area of the circle, what it's really asking us to find is dA dt. And so we'll start by setting up an equation for the area of a circle. The area of a circle is pi r squared. And if we differentiate that with respect to time, we're going to get dA dt equals 2 pi r dr dt. And so we can calculate this pretty easily because it says that the radius is increasing at a constant rate of 0.2 of a meter per second. This is giving us the dr dt. So we can fill that in here, but what's not given explicitly is the radius. we're going to have to figure that out based on the fact that the circumference is 20 pi meters. So circumference is 2 pi r, and if the circumference is 20 pi, then we can set that equal to 2 pi r and use that to find r. So if I divide both sides by 2, I'm going to get 10 pi equals pi r, and then divide both sides by pi, I'm going to get that r is 10. So now I have all the variables I need. So dA dt, I'll just kind of separate out this work here, over dt, this is the change in area over time, is equal to 2 pi times the radius, which is 10, times the rate of change of the radius, which is 0.2, and this is going to give us our answer. So 10 times 2 is 20, 20 times 0.2, really don't need a calculator for this, is going to be 4 pi meters squared per second. We're working with exact values here, so really don't need a calculator for this one. I suppose you could type it in if you just want to be careful with the arithmetic, the 10 times 2 times 0.2, but yeah, you really don't need it. Number 17 says the radius of a sphere is decreasing at a rate of 2 centimeters per second. At the instant when the radius of the sphere is 3 centimeters, what is the rate of change in square centimeters per second of the surface area of the sphere? So here we've got another related rates problem, and it's asking us for the rate of change of the surface area. Okay, so I'm going to call that, now they say, they're calling the surface area S here. So I guess I'll stick with that. Usually I call it area A, but since they're calling out the surface area as being represented by the variable S, we'll just kind of roll with that. So the surface area, what are we actually trying to find? Anyway, we're trying to find the rate of change of the surface area. So what we really want is, what is ds dt? So the surface area is given by 4 pi r squared, and if we differentiate that with respect to time, we're going to get ds dt equals 8 pi r dr dt. And it says the radius is decreasing at a rate of 2 centimeters per second. Be careful here. The fact that it's decreasing means that this rate should be negative. So just plug everything in over here. The rate of change of the surface area with respect to time is going to be 8 times pi times the radius. The radius is 3. I didn't call that out earlier, but that's given right here. Times -2. So on that number in particular, make sure that you recognize that the radius is decreasing. That is something that's kind of easy to miss, although notice how all the answers are negative, so I think you'd probably catch it once you start looking for your answer. But it is possible that they would have both positive and negative numbers down here just to kind of throw you off and make sure you know that decreasing means that rate needs to be negative. So 8 times 3 is 24, times -2 is -48. So this is going to be -48 pi, and our answer is C. Number 18 says let g be the function given by g of x equals the integral from 0 to x sine of t squared dt for x values in between -1 and 3. Which of the following intervals is g decreasing? Okay, so g is decreasing anytime g prime is negative. Or another way to think about it is when g, or the slope of g is negative. That's what g prime is anyway, but it's another way that you can kind of think about it. So what we're going to do is we're just going to type this equation into Desmos. So we're back on the calculator here. Let's exit out all this. We don't need any of this. And we could just type this in directly. G of x equals the integral from 0 to x of sine of t squared dt. The domain restriction that we are looking at is between -1 and 3. And so this is really all we need to look at. We want to know, where do we have a positive slope? So it looks like our positive slope is going to be everything from like here up to about here. So hang on. So hold on. Oh, no, sorry. The slope is negative. So actually we want to go from here down to here. So we're going from 1.772 down to, what is that? It's kind of going off the page here. Can I scoot this over? Let's see here. So we got 1.772 to 2.5066. Maybe I should make this a little smaller. No. Can I zoom out maybe? Then it's going to tell me. Oh, there it goes. 2.5066. So again, we're only looking for this little piece right here for where the slope is negative. And so we're going from 1.772 to 2.506. And so our answer is choice B. Number 19 says a particle travels along a straight line with a velocity that's given by that function, and the units are meters per second. What is the total distance? Okay, so not displacement, but the total distance traveled by the particle during the time interval 0 to 2. Okay, so total distance means that we're going to take the integral from 0 to 2 of the absolute value of v of t. If it was asking for displacement, you would not put those absolute value bars there. But because we're talking about total distance, we want to count all distance as being positive. So even if we take 2 steps forward and 4 steps back, our displacement in that scenario would be -2, but our total number of steps would be 6. So we want to count, all the steps as positive. So that's why we have those absolute value bars here. And now we just need to type that into Desmos. So I have the integral from 0 to 2 of the absolute value of, I need to type in Vt in there first. Let's get that in there. V of t equals 3 times e to the power of -t over 2 times sine of 2t. And what we want, that's a nice looking graph. Take a look at that. That's kind of fun. We want the integral from 0 to 2 of the absolute value of v of t dt. And so we get 2.261, and we find that our answer is D. Okay, number 20. It says 2 particles start at the origin and move along the x-axis. For t values in between 0 and 10, their respective position functions are given by x equals sine t and x equals e to the -2t minus 1. For how many values of t do the particles have the same velocity? In other words, when does the velocity of the first one equal the velocity of the second one? So what we want to do is come up with a velocity for each one of these. And just note that the velocity of a function is equal to the derivative of its position. So we're going to type in both of these equations and then find their derivatives. So the way we're going to type this in is going to be a little weird here. But basically what we want to do is we're going to type, basically call this first one, we'll call this first one f of x, and we'll call the second one g of x. It doesn't really matter what name you give them. But we're going to graph in Desmos is f prime. That's going to be the velocity. And g prime. And what we're going to be looking for is on that interval from 0 to 10, we're going to be looking for points of intersection. Okay, those are going to be places where the velocities are the same. So let's type in those two functions. F of x equals sine t, or I guess I'll call it sine x, and g of x, or maybe we stick with t's. I guess it doesn't matter. G of x equals e to the -2x minus 1. We don't need to see what these graphs look like. We're more interested in what the velocities of these two functions are. So to get the velocity, we're going to take the derivative of each one of these. So I'm actually going to hide these, and we're going to graph f prime x, and we're going to graph g prime x. We're going to look for points of intersection between 0 and 10. So let's put that domain restriction on here. So x is going to be in between 0 and 10, and I'm going to do the same thing for both of these. Okay, so it looks like we have a total of, here's one point of intersection. Okay, this blue one is the velocity of the first particle. The green one is the velocity of the second particle. We got one intersection point here, one intersection point here, so we're up to 2. Now we're up to 3, and that's it. So we have a total of 3 intersection points, which means there are 3 values of t on that interval where the two velocities are the same. So our answer is D. And that's about it for this particular one. On this, you should have been targeting 27 minutes for this, and we fell way short of 27 minutes. So, I think what I'm starting to notice is that the calculator problems here are not going to take as much time as the non-calculator ones, which kind of makes sense. But that also depends on how familiar you are with the Desmos graphing calculator and how to use it. If you know how to use it, you can definitely finish these questions in time. I don't think I quite made the time on the previous section with the no calculator. So that's something where I could probably go back and cut some time here and there, maybe on some of the explanation, but I think it's worth explaining through each of the problems. So if you're coming here, you have questions on those problems. So I want to make sure you get those questions answered. So that's it for today. Thanks for watching. Y'all have a great day.